Okay, I'm going to start. Lights okay? Too bright? Okay. So this is Tarski's theorem. So what I'll do today is, last time I introduced, the basics of complete lattices, partial order, complete lattice, and fixed points, monotonic functions, and fixed points, over monotonic functions. And those are very dear to us. Because reachability problem, can be expressed as computing different kinds of fixed points. And this is also a basis for, real basis for most automatic procedures for doing verification and so on. And therefore, I wanted to, cover this as well as the Kleene theorem. What the fixed point Tarski's theorem gives you is a characterization of fixed points of monotonic functions over complete lattices. It doesn't exactly give you a way of iteratively or algorithmically computing it. It just says when fixed points, that for monotonic functions, fixed points are guaranteed to exist. And the greatest and the least fixed points are will be unique. Okay, so that's the characterization. So it says, given a lattice and a partial order, the least fixed point of a monotone function always exists and is given by the greatest lower bound of all elements in the reductive set of F. A reductive set of F is the set of all elements in the lattice on descending chains. Okay? Chains, where since this F is monotonic, it is something on which it is decreasing. Okay, there is another version also. Okay, the greatest fixed point is similarly is considered as the least upper bound of extensive the set of elements on all ascending chains. Okay, and so if you want to look at it pictorially, yeah, this is what it is. So so this is the lattice, okay, and you have so this here are the ascending chains, and here are the descending chains of F, and for a moment, forget about this. This is one such a descending chain. This is one such ascending chain. So they have some special significance when we get to how exactly you compute. So this is the ext set. I mean, this is the reductive set, okay, where things are decreasing, and this is the elements on all ascending chains. And this one, the intersection point here, is where all the fixed points lie, okay, which is one. And this least fixed point is the greatest lower bound of all the elements on the descending chains. Similarly, the greatest fixed point is the least upper bound on all ascending chains, and that's what that thing says. And what Kleene's theorem says is, under certain conditions, that the least fixed point can be computed as the least upper bound, the limit of a specific chain in this, where you start from bottom and you keep applying F iteratively. And similarly, if you want to compute the greatest fixed point, then you can start from the top element and repeatedly apply F. And you're guaranteed to converge in the limit to the greatest fixed point. Okay. there is an additional condition of, in addition to monotonicity, you have to require continuity as well, and we'll get to that. So here's just to give you what are the kinds of elements. So I'm just putting some illustration here. So these are all the reductive chains, okay, elements on the reductive, descending chains. And you can have similarly here, and you see they all end up in some fixed points there. And among them, there is a greatest and the least fixed point. This part, which is at the intersection of the greatest and, the reductive and extensive chains, also have those stop and because as it sees, as a consequence of this itself, the elements which form the fixed points themselves form a lattice, with the top element being the greatest fixed point, and the bottom element of that sublattice being the least fixed point. So some of the elements that are not in either the extensive or the things are things like this. Okay, you can't have elements, incomparable elements in the function they cannot be there. Although that is allowed, in monotonic functions, you can have things like this, but these kinds of chains are not permitted because that violates monotonicity property. So this cannot be, if there is such a chain, a monotonic function cannot produce such chains, and that's why, the fixed points are guaranteed to exist at this intersection. Okay, and that's what the proof really involves in showing. Yeah, we'll show the proof for this case, and similarly, you can prove for the greatest fixed point as well. So any questions here about the statement or the concept of fixed point and so on? Okay. So, like by definition, Tarski says is that the greatest lower bound of the reductive set is the fixed points. So, of course, fixed points are of a function are all those elements for which every element x, for which f of x is equal to x is the fixed point. So the least of that, we want to show that it is equal to this greatest lower bound. Yeah. Last time. So the greatest and least upper bounds, they are what is called join and meet. Okay, the least upper bound is called join, and the greatest lower bound, I use them interchangeably, is what is called meet. Okay, so once you have a partial order, these things are defined, and in complete lattices, every subset is guaranteed to have a join and meet. Okay, I prefer to call them the greatest lower bound and least upper bound. What do you mean by isolated elements? Yeah.
Are they still subject to join and meet? If they're subject to join and meet, if I take join.
Yeah, they are subject to. So, yeah, just because the function, so there are two kinds of things. The dotted here are the partial order. The solid arrows are what the function maps. Okay, the operator maps. It's the function that is mapping, like in elements like this. The function, a monotonic function, can map incomparable elements. Okay, so it only requires that if x is less than or equal to y, then f of x should be less than or equal to f of y. That's what it requires. Therefore, it doesn't preclude f from mapping this thing. So these kinds of elements can be there, but the rest of them will have to be in a way consistent. Okay, the rest of the elements, if I haven't shown exactly, okay, you cannot have this thing like hanging in the air, because everything has to be the thing. If tau is mapping something below that to something below than tau, then there will be some constraints as to how this thing has to be linked. I haven't shown that, but it doesn't preclude the existence of these kinds of things in the map of things, just like something that I'm showing here. Okay, that's all. So yes. So yeah, they are. I haven't shown all the dotted lines. So I'm assuming that's why I said this whole thing is a lattice, is a complete lattice, which means that the partial order will be there. Okay, and since it's monotonic, in these cases, for all descending chains, the dotted line and the solid lines coincide. Okay, they are also related by dotted lines. So in some cases like this, these are incomparable, but they can be dotted lines from top or any one of these elements to either of these incomparable elements. Actually, they will have to be there. Okay. Otherwise in some F may not be monotonic, but I'm just saying that these kinds of things will not be there. This is certainly one situation where the monotonicity of F is violated. Okay. In this kind of case, because you see these two are this one is less than this, but this maps to this and this maps to itself, and therefore they're incomparable. So that violates monotonicity, and that's kind of a thing where these kinds of things will also be required to be outside of the thing. Yeah. Okay. So the proof is broken down into showing two inclusions. Okay, that every and every is in the reductive set. As a matter of fact, every fixed point is in the reductive set, because it is a fixed point. F of any fixed point, particularly LFP of F, is equal to LFP of F. Therefore, it has to be less than or equal to that. So the real thing is, proving the that red F itself is a fixed point, and it is within this thing. Okay, see, both the greatest and least fixed points, which is the greatest lower bound of all these things, itself is in that set. Okay, that itself is the fixed point, is the second thing that it shows. And since once you show this, and since LFP is always in the reductive set, and this is the greatest lower bound of all the fixed points, and therefore that is also the least fixed point. So what remains to be shown is that indeed the greatest lower bound is a fixed point. Okay. And that's what is shown here. Okay, so the first part shows that F of, this is the greatest lower bound of the entire set, is when you apply F is less than or equal to that. And then this one shows that the other direction, and because of anti-symmetry, this becomes equal. So what is this? This is the greatest lower bound of all the elements of the lattice in descending chains, and therefore this has to be for every x in that set, in the upper set, that in the reductive set, this must be less than or equal to x. And by monotonicity of F, if you apply F to both sides, F of that greatest lower bound will be less than or equal to x, and this is true for every x belonging to that. So this is kind of another lower bound of every element in that set. But by definition, this is the greatest lower bound. Okay, therefore this has to be greater than or equal to that as well. This one, and that's why so this is also equal to less than or equal to that, which means that this f of applied to its greatest lower bound. I mean, yeah, this less than or equal to follows from that the fact that this is the greatest lower bound. Okay. So as you can see that the greatest lower bound of the reductive set itself has to be inside in that reductive set. So to show the other direction can be shown by using this, the fact that it is the reductive set and monotonicity of F implies that's what. So as I said before, so this f of this itself is in the reductive set, because if you can apply f to both sides, it is going down, and therefore it is in the reductive set. And since the greatest lower bound is less than or equal to every element in the reductive set, and we've shown that f applied to this thing has to be in there. So we've shown that the greatest lower bound is less than or equal to that. So that is a fixed point. And so it has to be inside, and it is also a fixed point. Okay. See, this shows the existence. So Tarski's theorem does not use any additional condition like continuity requirement. Okay. It's only the Kleene's theorem that requires f to be continuous for you to be able to compute the least and the greatest fixed point in a certain way. Any questions here? Yeah, so this shows that f of red of is this. So f of red of s is less than or equal to f of this, and that's why it shows that f, and that is due to monotony. It uses this part, and therefore it implies that f applied to this itself has to be reductive, and since this is the greatest lower bound, this must be less than or equal to that. Yeah. Oh, because of A, we have just proved that F applied to this is less than or equal to this, right? And due to monotonicity, if you apply F to both sides, okay, then f of red of F is less than or equal to f of red of F, which means that f of red of F is on a descending chain, and therefore it has to be inside red of F, inside the reductive set of F. Okay. And since this is the greatest lower bound, we get that this is less than or equal to that. Yeah. No, just put y to this. Make this as y. Here it's saying f of y is less than or equal to y. Okay. So f of, and since f is monotonic, if you apply once more f to it, f of y, which is f of y is less than or equal to f of this has to be less than or equal to y. Okay. F of y has to be less than or equal to y. Okay. Yeah, and that's the y here is f of red, and because that is less, okay, it is going down. Yeah. So it's on a reductive, y is in the reductive set. Yeah. Yeah. And y here is f of this. And since this is the greatest lower bound, it has to be less than or equal to something which is on the reductive So once you prove that f of applied to this greatest lower bound is reductive, which is what this implies, okay, due to monotonicity. Why? Yeah.
F, you have that f of y is less than or equal to y, apply f on both sides, and then you get that f of y less than or equal to
No. I'm denoting.
You're denoting intersection of red and as y, right?
Yeah. F of y, okay. Yeah, and then f of y is less than or equal to f of y, and therefore f of y is reductive. Yeah.
Yeah, the lower bound of red would be
Correct. Yes. Yeah. Yes. Now I'll come to this a little bit later after showing what. Yeah. So here, this is, this set is usually called post fixed points. Okay, the ones in the reductive set, and these are pre-fixed points. Okay, that is just for reference, which we'll get later on. That's pre and post, and you see. So, yeah, now we will talk about this once. Here I showed that this greatest and least fixed points can be computed as by doing this, following this particular chain of iteratively applying f, starting from the bottom element to itself, okay, to f. And that is, and if you did that starting from top, you get the greatest fixed point and the least fixed point with some condition. And that's what before I do that, that's what Kleene's fixed point theorem says. Okay. So before that, let me just clarify. A chain is a total ordered subset in the lattice. That is, for every S1, S2 belonging to a chain, either S1 is less than or equal to or S1 is greater than or equal to S2. So then you have this concept of an ascending chain, okay, where every element is related as by the less than or equal to as the index increases, and the descending chain, this is height of the lattice is the longest chain, etc. Okay. Yeah, if the elements of your lattice are sets of states, subsets, the power set, the domain of a universal set of states related by the inclusion operator, relational operator between sets, then any chain here gives k reachable states from the origin state. Okay, and all our application of this theory will be for the domain in which the element, the lattice, the domain is, the elements of the domain are, the domain is the power set domain over the universe of set of states. So what is continuous? This you probably most of you already know. So it is continuous with respect to the least upper bound if there is a function from two mapping elements of a lattice x to y, then f is continuous basically if f is monotonic and preserves the least upper bound, which I also refer to as the limit of all ascending chains. Similarly, it is continuous for meet if it preserves the greatest lower bounds for all descending chains. That is, if you have a chain in the domain X and you apply f to each element, okay, you get an f chain over there, that in the limit, those two should be preserving. And that's what this thing here pictorially it shows. So this is a chain in the X domain, and this is f is monotonic, and therefore it all has to go in a also has to be an ascending chain if it's an ascending chain here. And this is the greatest, the least upper bound in this case. In that case, the F should map to the least upper bound of this chain as well. Okay. What cleaning iteration that I showed in the previous thing says is this, applies to a particular chain, okay, where F itself, is applied iteratively to a thing. We'll get to that, yeah. Yeah, so the cleaning fixed point theorem says the least fixed point of a monotonic and continuous function can be computed as the least upper bound of an ascending chain of repeatedly applying F to itself, starting from the bottom element. And the greatest fixed point is the least upper bound of the particular descending chain. That's all. So here's a proof of that. Yeah, intuitively, why should this be true? I look at this, or I can even look at this. This is already here. See, if it's a finite lattice, it is kind of obvious, no? So because if there are only finite elements, you can't keep on. And, anything else, if you start from bottom, if you keep applying F to itself, since F is monotonic, that automatically gives an ascending chain. I mean, if it is starting from bottom, and you can't keep on in a complete lattice, you can't keep on doing this because every subset has an upper bound. Okay, and in this case, the least upper bound is the upper bound of this set of elements on the chain itself. And then, and if you started with anything which is, greater than bottom, obviously that would in the limit be, its upper bound of that chain will be greater. Okay, and if it's an infinite case, this cannot keep on going forever. And at some point, it has to fold into itself. Okay. So it's the finite case. So the only time where it can get violated is if this is a dense set and then it's an infinite lattice, and it's also dense in the sense that there can be kind of local limits, maybe, or there's discontinuity in this at some point in the ascending or the descending chain. There is discontinuity, and it can jump, and then that can result in in a divergence of the limit and the this fixed points, and that's what continuity is. Condition is guaranteeing that even if there is, as long as there's no discontinuity in the thing, that's what this thing is saying. Okay, it has to preserve the limit. Every chain, if you take in this case, the least upper bound of any chain here and apply F to every element in the chain, and in the limit, this limit, or that's the least upper bound, F will be such that it will, the least upper bound of the F chain will also be the thing. So, this gets violated if there is discontinuity somewhere in between. And once this is preserved, then intuitively this thing is guaranteed. Okay, here is the proof. So as we know, by definition, the least fixed point, Tarski's characterization, says the least fixed point is the greatest lower bound of all the elements in the reductive set. Okay, we already had a proof of Tarski. So what Here it's shown is that what Kleene's theorem says is that the least fixed point is the least upper bound of this possibly infinite ascending chain. That's the limit is, yeah, it's the least upper bound of that chain. Okay, so the first part is showing that the least fixed point is less than or equal to such a limit, the F chain limit. See, for every I, because of monotonicity of f of I must be less than or equal to f of I plus 1. Yeah, because we're considering ascending chains. Yeah. So this proof is an ascending chain. There is a similar proof for descending chains. So f of then you, and this is by monotonicity. Now you could, what if you apply, now let's suppose you apply f to the least upper bound of this chain, fi of bottom. That is equal to this by continuity. So continuity says that f is limit preserving. Okay, therefore f applied to that can be computed by computing the least upper bound is the same as the least upper bound of the f chain. Okay. Right, this is f is moved here, but when you move f, because this is special chain that you're applying it to, which is iteratively computing, the limit of f of a chain f of I plus 1, you do one more, is the same as I tends to infinity, and therefore you get f of applied to the limit is the same as the limit of f of I. And so once again, this is in reductive set. And so you get from the same thing, since that is the x hat is the greatest lower bound of this one. So I've shown that this limit itself is in the reductive set. X hat is less than or equal to that. Yeah, so it's basically saying as long as there's no continuity, this has to fold in itself. It is showing the other direction is can be done by induction. Okay. Yeah, that x hat, as per Tarski's characterization, that is the greatest lower bound of all the elements of the reductive set, is greater than or equal to every element in that Kleene ascending chain. And that is done by induction. Okay, so when I is equal to 0, f of 0 of bottom is bottom. Therefore, everything is, bottom is less than or equal to everything, including x hat. For the induction case, if you assume that fi bottom is less than that, we need to show that if when you apply one more, do one more iteration of applying f to that, which is f applied to fi is thing. Now, for this hypothesis, you apply f to both sides, and you get this because of monotonicity of f. And f of x hat, since x hat is a fixed point, which is what our starting point is. Now we have to show that the fixed point is, here it's equal to the least fixed point. So since x hat is a fixed point, this is equal to that, and therefore we get that f of I plus 1 is less than or equal to x hat. Okay, that is x hat is greater than. So that's the end of the proof. No. Let me. Okay. Where does, just to show an example, I don't know, maybe people who have seen continuous functions, and a lot of people might have seen this proof, but for the others, where does discontinuity screw things up. To illustrate that, I have two examples here. So here f is a function. Both of them are functions over real numbers, or some subset of real numbers here. So here, f of x, as long as x is strictly less than 0, it maps it to 0. Otherwise, it maps it to x plus 1. So there's a discontinuity at 0. F has a discontinuity at 0. If I ask the question, this is not a continuous function. I mean, the test for a continuous function is this one. If you take a chain, every chain, when up, if the least upper bound of every chain, when applied to, when you apply f to that, it has to be the least upper bound of the chain that you get by applying f to every individual elements in that chain. And take this chain starting from minus infinity all the way to minus 1, and then you get all the way to fraction thing, and then you keep on going. So the limit of this, that the least upper bound of this chain, it converges to 0, right? Yeah, that is the least upper bound. But since there is a discontinuity, that gets mapped to 1, okay? Whereas if you take simply, apply f to each of them, and you can see all of them will get mapped to 0, okay? Because that's the way the f function is defined. Therefore, this is a 0. And so, so that is not, and in this case, there is a fixed point. It is infinity, okay? The fixed point of f is infinity. I'm assuming that R is enhanced with top and bottom elements. Yeah, here is another example where there is a discontinuity. Here I'm using the R plus the positive domain with enhanced by a bottom element 0. So it doesn't have infinity. There's a top element, the bottom element 0, and the discontinuity is at 2. Once again, similar to the reasoning here, the f is not a limit preserving here. So if you can take this chain of 0 to something which is less than 2, that converges to the limit 2. So but f of 2 at 2, there's a discontinuity, and therefore it gets 5. And when you apply f, each of them will be less than 2, and therefore they converge to 3. In this case, this chain indeed computes infinity. Okay, just there's no guarantee. So the continuity sometimes may not be required. Okay, the Kleene chain may still compute the greatest fixed point. That's because there was no local fixed point in this case, and that's why that is one of the reasons that it does. And that shows, at least the first example shows, that continuity is indeed required. Yeah. So any questions so far? Okay. Okay, now I'll go back to showing how it is used in our case. So for reachability computation. So as I said, the state space for us is, there's a universal set of states, and there's an initial state which is a subset of that. There's a transition relation defined as a binary relation over that set, and in the case our lattice is sets of states. They are intended to represent some result of some reachable sets over this transition system, and they are ordered as per the set inclusion. And we have a post operate. I mean, here I'm showing you one example of how something computing the set of all reachable states from an initial state can be represented as a fixed point. We've already seen that in the case of strongest post condition informally. And what I'm going to show here is kind of precisely the function for which this is a fixed point, okay? That the set of reachable states reachable from any one of the initial states, okay? So, and I'd shown this before, so I'm not going to belabor this. So there's post, which is exactly what I had said is image of some set X. This could be a formula characterized by a formula which is mapped under this relation R, which forms the transition. Given that, then this is the accumulator operator. Okay, I call this the predicate transformer or a higher order function because it is mapping sets to sets. Okay, and here our fixed point is the reachable set is an element of this lattice, which is computed as expressed, characterized as a fixed point of this function, higher order function. What this does is, all it does is adds I to the post of X. And the set of reachable state is exactly the fixed point of such a higher order function. Sometimes the least fixed point is represented also in this fashion, in some, let's just lambda x of f of x. So it uses the post operator, and it is this function represents one step in that accumulation. So if you used, and this is obviously monotonic, right? Why? It is adding, something. Okay, if X is two sets are less than or equal to that, it is adding, the image. If X1 is less than or equal to X2, the image of X1 is obviously less than or equal to X2 under R, to which it is adding I, and therefore it is monotonic. So once you have monotonic, the previous two theorems guarantee the existence of fixed point. Okay. And in particular, here, of course, you have to show the continuity as well. Since for our application, if we assume it is our domain is finite, then monotonicity automatically guarantees continuity, and therefore the released fixed point can be computed using Kleene iteration. Okay, and that's what here it is done. Okay, this is at the basic core, model checking algorithms, at least symbolic model checking algorithms, do this for invariant properties. Okay, so you start with, so f here is defined as I've shown here. Yeah. So f of 0 is empty. Yeah. Why? Why is f of 0 empty? F applied to bottom. Actually, it's wrong, isn't it? No, f of 0, that is, start with f of 1. Okay, f of 0 is, by definition, is bottom. Okay, yeah, so that is 0 iteration, so you're not applying anything. So that is, bottom in this case is the empty set. So when you apply once, because the post of an empty set is empty, so this gives rise to I. This is how you kickstart the Kleene iteration. So you start with that, and then you grow it. Okay, each time adding to X. Okay, the previous f of I, fi in the I plus 1 step, you're adding the post computed over the result of the previous step, okay? And so on. So this is basically, there is some redundant computation in the way that you do it here. And I think someone observed it when I showed right in the beginning. So I is kind of repeatedly added. Okay, there are lots of optimization that you can do. So here you're unnecessarily computing image of redundantly computing images that you already have it in there that keeps getting repeatedly included, and therefore you could take in each step the difference between that, and you can compute the post. But nonetheless, this is such iterative computation, you can actually prove that your fixed point that you get is indeed the reachable set by induction. Okay, so that's why sometimes expressing what is being computed this way is easier for proving correctness of your the fixed points when computed accomplishes what you what you want, what you intend it to accomplish. Okay, and that you keep iterating this until you can't until you reach fixed point, which itself can be checked by checking this one. So all this, as you can see, the post computation, the image computation we already saw can be expressed as an existential, using an existential operator. The union as an OR. And this is the fixed point check is implication. Okay, and that's what this does. And it's the most expensive part here is computing the image, okay, because that is existential quantification, and that's where you could end the various other engineering activity where you avoiding redundant computation, etc. So a lot of these things, optimization to model checking, symbolic model checking algorithms, like in how you represent these images, how you do existential, the pre-image or image computation efficiently over your required domain, etc. So that's where the nitty-gritties of implementing the symbolic model checking tools address, and the challenge lies. Okay, this I've already seen, so this I'm going to skip. Okay, now let's see. I still have 15 more minutes. So what I'm going to do is some more fixed point transformers. Okay, set of reachable states starting from an init, and that is the strongest inductive invariant for a T. So in some sense, it is this, the reachable set is the strongest that you can say about inductive invariant that you can say about a transition relation. How do you do this? What is, okay, there are, okay, when you want to express the strongest post condition here, this is kind of being applied specifically to a while loop. Okay, so that I'm saying. So a while loop has a transition relation which maps, the pre and the post states of the body, and there is a loop entry condition LC, and you want to compute a formula which is for a given this, which is the while loop, okay, represented as symbolically, you want to compute the strongest post condition of this particular predicate pre. So what does this imply? You have to come up with a predicate transformer of which the strongest post condition is a fixed point. Okay. Yeah, but once you come up with the appropriate predicate transform, you have to design the predicate transformer, correctly. That's where the cleverness is. Computing the least fixed point, I mean, whatever that you compute, if you compute it using clean iteration, is guaranteed to be the least fixed point. So the challenge lies that you will have to have one step of that, which is what is captured by F, has to be done precisely. Okay. So what could this be? I mean, I think this we have already seen. So I will do, yeah.
Predicate transformer of which this would be a
No, a loop invariant. Okay, I'll answer that. A loop invariant is a fixed point of F. Now, what I'm asking you is there are so many loop invariants, okay? Right? So this procedure, cleaning iteration, is set up to actually compute any fixed point that you want to compute, okay? So that is computed by defining an appropriate predicate transformer of which the fixed point of which will be your loop invariant. Okay, that's what I'm saying. So my question is, what would be that loop? And what would be that predicate transformer? Okay. So I mean, I don't have it written here. Yeah, maybe I'll write it here. Yeah, the first should be what? Get, since I don't have a board here, and since they're so this will have, I mean, as parameters for a given tree, transition relation, and a loop condition. Okay. Yeah, that's kind of the parameters. What should this body be? Okay. So what would be the init? The I was the initial state. Here it's pre. Okay. So I'm saying I'm already giving you a clue that it has to be some post. Okay. Usually for doing it in the forward direction, you would use image, and for doing it in the greatest, if you're doing of a computing the greatest fixed point, it has to be pre-image or some variations of those things. So the first thing is, okay, let's suppose that I'll give you a hint. You can use image. Okay. So in one step, okay, you start with the empty. What is the first iteration, the set? How will you represent the set of states that you get after one iteration? The idea is you have to accumulate the states, the set of states that you get the strongest in images that you get for each of the iterations. So I've already given you the transition relation for the body. Okay. Let's suppose that thing is.
It will be something like image of tree under T comma body, T body.
Image of T under, that's T body. Now, if I'll assume it's T body, okay, of Okay. If it is 0 iteration, then it has to be ANDed with not of LC. That's where the LC comes, okay? Because if you can exit, is that clear for you? Yeah. So what would be the next iteration? So this is the set of states that you get from 0th iteration, right? Okay, actually, no, I'm sorry. It's even wrong. I wrote it wrong. So 0th iteration is just pre and not of LC, correct? If you exit a loop without doing any iteration, what is the strongest, post condition? You just not LC, the intersection of not LC and pre. That is what 0th iteration is. No, because the pre can have states that require, there may be some states, some subset of states where you exit the loop in after 0 iteration, some after 1 iteration, some after 2 iterations, and so on. Not all loop iterations have to be for loops, okay? So there could be some inputs where, I mean, look at sorted array. Sometimes if it's completely sorted, it is, you exit after 0 iteration, don't you? Yeah, Sawmill? Yeah. So there's a whole bunch of states in the pre, okay, for which you could exit the loop in 0 iteration. So it won't be just pre, okay? So the pre state can have those states in, for which you need 0 or more iteration to exit, okay? That is generally true. I mean, for some input conditions, you require not all input conditions you exit after 0. As a matter of fact, only a small. Yeah. Yeah. So that should be, okay, it should be, in general, an arbitrary step. I mean, intuitively, if I want to give, I could state it as, oh, my strongest post condition should be the fixed point of f. Any f that you could devise that is a fixed point of f would be fine. But intuitively, what should that do? It should accumulate states in pre that get exited after 0 iteration. Those states that, um, iterate once the body of the loop, and then LC gets violated and gets, it does one iteration of computation and gets exited. Okay, that should be in the in your in your strongest post condition, right? And 3 iterations, 4 iterations, and so on until you accumulate over arbitrary number of iterations. And that's what F should, that one step of that is what F should capture. Okay. That's what I'm saying. Okay. So
Exit after exactly one. Something.
no. F should be after an arbitrary iteration. So I'll be defining it as, say, F given some X. Okay. Yeah, I mean, let me define it and maybe you will, let me define it and explain why it is. So it will have this, okay? I mean, you remember that how I defined for reachable state. I use the initial state and the post image, right? So now you could do this as plus, that is the union, okay? This is exactly the post, yeah? So what happened was init. Okay. So this is what this thing is. Huh? Yeah. I mean, I'm using, yeah, I'm lazy. I'm lazy. T body, yeah, T is the same thing. Okay. Now, oh, this is actually wrong. So I have to, if you want one more, okay, so it has to be, after that, it has, this is a general image, okay? So if you want exactly one more step, you should have not of LC, okay? Yeah, this is what I'm claiming, yeah.
What F is supposed to be. I'm not asking. I I understand if, like F, but I'm asking whether F is supposed to be what happens after one iteration in some sense. I'm not sure. That's what
No, this is not the weakest precondition. This is the strongest post condition. Strongest post condition. What it has to capture is what should, if you want to talk intuitively, that it has to capture what needs to be added in this chain. Each time you're applying F, you're doing cleaning iteration, yeah? So each time you're adding something to F, okay? So that should be for an arbitrary iteration. So if X is your, like a continuation, okay? So if X is something X, okay, the input that it gets X is, F is mapping X, some set to a some set. So if X is something that you get after I iterations, you should, then it should define what it should do to add to that, okay? X. X is a set. It's a set of states. It's an element of the lattice. F is a higher order function. Okay. So F maps set to set or formula to formula. So I'm defining what you asked me what F should intuitively be doing. Yeah. Yeah. But in this case, that initials, yeah, like, no, in this case, that is, okay. No. You see, it is not just pre. I mean, I just said, so that's why it has to be pre and LC. It is defining what you would get if you exited, okay, in zero step, nah? So it is not pre. It is, though init what you had there. Here, it is the post predicate set that you get exactly if you started from pre, and you exited without executing the body. That is the zeroth iteration. That is your init. And that you always should have. Okay. To that, I'm adding something which you would add in an arbitrary iteration. If you had already computed up to a certain IF, then you're adding that. Okay. What would FFFFX is? I actually showed you that for that. So I actually showed you that you could do that. I mean, I think I showed you this one in thing. Now here, so yeah, this is what it does. Yeah. Yes. Yes. And that's the post. Post is image here. So as I've done here, I haven't shown that here. See, this is exactly F. Given an X, it is doing adding I to post. Post is exactly the image of X. So that is, it is showing what is it that I'm adding in each step of the cleaning iteration after at an arbitrary point. Okay. Intuitively, that's what it is. Yeah. Since I know that each time I have to compute the image of the what have accumulated up to that point, which is what the argument to x would be. Okay. Since I'm applying, repeatedly. And I thought your question was how exactly what happens when you repeatedly apply. Yeah, but you don't know how you got this? Huh?
In my mind, perfect is the condition that we get when the loop terminates without entering or executing it once.
No. See, f of 0 is bottom, okay? Here, f of 1 is if I did one step of t, okay? Yeah? So that is, I mean, actually zero step of t. Huh? Yeah, that's right. And then that would be zeroth iteration. You're not applying t at all, okay? So this one is frivolous, okay? This one is actually zeroth iteration, huh? Because then it will be initial. In the case of post condition, it's slightly different because there is an exit condition. Huh? So whereas here, yeah.
The image of t.
No. I did not. I didn't. Oh, did I? Okay, then it's a mistake. I thought I wrote. Yeah. I know. I mean, there. If I made a mistake, then I'll see. No, I just wrote P of n naught of LC. I think I would close it here.
Say that I P and not L, P and not LC.
Yeah.
And post is image P and not LC. Yes, I mean, I think this is slightly different.
No. See, the reason that here's my argument. Because this is each time you have to check the LC condition. Now, if you had checking of LC in the T body itself, then it would be just image. Okay. Because each time when you execute, what are you executing in each iteration? You're checking if after you do an ith iteration, if whatever state that you're in, if you're entering LC, oh, it should be LC, I think. No. I think it's okay. So, yeah, here you are computing for an arbitrary thing, right? So since in T body, I'm assuming this is something that I do not have. If I, in T body, if I had, if LC do this, else keep it the same, then I don't need this, okay? So since now I'm computing the image over those states in which it would have exited as well as not exited, okay? So I have to do LC actually on X, okay? Yeah, that's what I'm saying. Yeah.
Second part, the possible states after which are achieved after exiting after iterating once, right?
No, not once. If you are at a state after executing I iterations, okay, then if you did one more iteration, what it would be? No. Why do you say I is equal to 1? See, this one, I will be applying as f of bottom.
An example code. I wrote simple. X is 3 x equals to 0. And my loop and my condition is while x is less than 10, x equals to x plus 1. So I'm just incrementing x until I reach 10. How will this look? Because P will be x equals to 0, and not of LC will be x is greater than 10, greater than equal to 10.
Yeah, so here what I'm computing is I'm repeatedly computing, okay, since I have I added in the thing, so I'm repeatedly computing the image of all the things, okay? So in each step, I'll be computing, you're right, okay? I'll be computing because of the way that I have embedded the I right in the beginning. So in the I plus one step, I'll be recomputing all the things, okay? Because I would have added I so many times, no? Yeah.
Not LC is greater than equal to 10. That would just not, there won't be any state like this, because I'm giving two different directions over here.
No, 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 no. Why would pre and not LC be empty? Huh? No, no, X, if X is bottom, yeah, X is bottom means false, no? That's empty set. Huh? Yeah, this one is pre of, yeah, in the beginning, this will be empty, okay? Now, if I have, yes, okay, what you're saying is if X is bottom, let's say maybe, yeah, so here it was bottom, post of S was bottom, and there was I union post of S, no? So maybe what is, so when I put X here, when it is bottom, so X is being put here. This I is like a constant, okay? Like it's a predicate, nah? It's a predicate. I'm doing it as a predicate. Therefore, if I say it is, you know, here also you could ask the same question. Why I'm applying I to X. I'm not applying I to, I mean, I'm not applying bottom to I. How did I get I here? Because it is I as a predicate itself, and post of 0 is a predicate, okay? And you take the union of that, and post of 0 is all I am applying that X for, okay? In the next iteration, of course, I'm applying for this entire thing, okay? Like I'm doing here. That's why you get I union post of I union post, okay? There I'm applying. Therefore, what Ayan said doesn't apply, because see, if you said, oh, I apply to bottom, to that I'm not applying, because that's already a predicate, nah? So I'm taking a union of these two predicates, and or maybe what I should be doing here is, okay. I think I see what the confusion is. So, no. I think this is correct, okay? So I'm using pre of LC as a predicate itself, okay? And, you know, X is only being used for this purpose. Okay, so here, of course, I will compute whatever I got from the previous thing. So here I'm not applying X. So when I move from zero, empty, the zeroth step, to the first step, this will just be added as a predicate by itself. You're not convinced?
I will be convinced if I see if I can get a definition for what this thing is supposed to be, not just an expression. That's all.
What do you mean? This f of x is supposed to give, see, it's like x is a predicate. Yes, so yeah, so here I'm applying this thing for this, yeah, image I'm computing, and this one will be, okay, this is what I'm saying, yeah.
current value of x.
Yeah, I'm sorry. Yeah, here the type is a little bit confusing, isn't it? But here X itself is a, a predicate. Therefore, this has to be, so this is okay, isn't it? Huh? Yeah. So what is the confusion here then?
Take a definition and work with it, but I understand it.
So, I mean, I think if it, okay, let's first, okay, I know it's getting late, so 6:24. So I'll only, so in 5 minutes and then we can do this. Let's look at this. Okay, is this, maybe there's some syntactic mistakes there. So here it's clear, no? Yeah, but I think you had, so X is a either predicate or a set. Okay. I is already a set. Okay, predicate. So you could now have, if you had X put in there, okay, which will be each element of that domain, then that I'm not doing. So I can stand on its own. Yeah. So now to that I'm adding just the image of whatever I get with X. X is what I call as continuation, which I got as a result of accumulating over the previous I steps. Yeah. Computing in the I plus one step, I'm computing just the image of whatever is passed on to that X, to F. Okay. So so that's why when you ask me what exactly is this doing, it is taking what I call as a continuation, which is what it has accumulated over I steps, and determining what should the result of the I plus one step should be. Okay. That I'm saying you keep adding the initial state all the time, which is what is counterintuitive. Okay. So you will have to compute the image of whatever X is. I'm saying you compute the image of whatever input, which is the continuation that I get. And then to that you continue, you add I. Okay. So if anything, the image computation is kind of intuitive. Okay. It is why you keep adding I all the time. Haven't you already computed the image of I? Was kind of the question that I thought that you were asking. Outside of whether the strongest postcondition formula is type correct or not. Okay. So you don't need to apply. I mean, you said, okay, F0 is empty. So in this step, the fact that X is applied to, oh, it's not applied to I. Okay. Huh? You get I. Similarly, pre and not LC, you get pre and not LC. Yeah. Oh, which is where you're from, because it doesn't type check. No, okay.
Second union, like the second argument of the thing. Yes, that is what we were having a doubt about. Why is
Did not have this.
yes? What is the point of that? I am not saying that we don't have it. I'm saying I don't understand why it's in that.
Yeah, but that's what I'm saying. Okay, then I would do this. If T bar Okay. So maybe, so I will write it down with some thought and then we can discuss. Yeah. Okay. So you're saying regardless of whether you include LC inside this or not of LC, you're not convinced that it will result in the states that the post state that you get after I plus 1th iteration is what you're saying, right? Yeah. An arbitrary I plus 1th.
Inside, like what we wrote before.
Mm.
If we write that, then I think we will never get.
Yeah, but even with not of LC outside, you won't get, is what you're saying?
Then I consider the loop conditions. We have to somehow consider it. Like,
Yeah, I think I have two things. I mean, first, I was claiming that these two are equivalent, but I will check and then we can discuss next time. Okay. This was what I thought was there are two formulations I have. One is this formulation, okay, and the other formulation which I thought was an equivalent formulation when I expand it out. I mean, you can actually check when you expand it out what it gives, and we can actually settle it. Okay, this was equivalent to having LC inside. If LC, then the body as the formulation of the transition relation. Those two are equivalent is what I thought. So, let's resolve that. Okay, next time. Yeah, okay. Yeah, similarly, if you also thought a little bit, okay, which is what we'll do it next time, okay, for computing the other two things that I have is similarly for the weakest post condition, okay, weakest precondition, okay, how you would do. If this can be expressed, once again, you have to be careful about the loop condition here, okay. How exactly do you take that into loop condition, which was not the case when you had an arbitrary transition relation where you were doing it infinitely, okay, whereas here you exit, and that's what makes a little bit of a twist. The weakest precondition to the formulation, as well as K induction. Okay, both of them have to be expressed, are more conveniently expressed as greatest fixed point. Sometimes you cannot express everything as doing linear iteration in the forward direction. Okay, so that is something that I want to illustrate as well. Sometimes, I mean, you can't always. No, I take it back. Anything you can always express as least fixed point, but sometimes you'll have to guess the initial thing. Sometimes here the strongest post condition was naturally expressed as linear iteration in the forward direction, whereas think about how you would do K induction. Okay, so the reason is they are naturally expressed of the thing. So in the K induction, what you're doing. Sorry, since you're going from P to something which is smaller. Okay, so in the forward direction, if there was some init state, I could do this. Okay, so whereas here P is not doesn't work like an init state, and therefore you will have to do it in the backward direction, because what you get as the result, if you somehow could guess this P hat ahead of time, then you can go ahead, or something which is close to that, then you can do it. And therefore, sometimes you will have to express it as backward thing. So, we will do that. So think about this, and also think about the solution. Maybe I've made a mistake in the actual formulation. So we will settle it next time. Okay, thank you.